Good afternoon, everyone. Welcome to Solmax, and thank you for joining this webinar session today. Today, we'll be looking at asperity height or asperity concentration. What matters more, or what can help us if we want to increase interface shear resistance along a geomembrane surface? A little bit about Solmax's webinars. We rolled out those webinars just about a year ago to be able to share helpful, reliable, unbiased information with the industry on designing with geosynthetics and on designing with geomembranes. So all of our webinars, we do have a few of them already. You can access them online on our website, www.solmax.com/en. My name is Doyin Adesokan. I'm a technical manager here at Solmax, and I come from an engineering background into this role here at Solmax. I'm registered in Saskatchewan, Canada with the Association of Professional Engineers and Geoscientists of Saskatchewan, and I will be your host for this webinar today, hopefully the next 30-35 minutes of the webinar session. So, an outline of the presentation, I'll look at should we texture or should we not texture? Also, should we texture HDPE geomembranes or should we not texture HDPE geomembranes? If we need to texture to increase our interface shear resistance along the geomembrane surface, what can help us? Should we increase the asperity height or should we increase the asperity concentration? I'm going to share with you some studies that have looked at the contribution of asperity height to interface shear resistance or interface shear properties. And I'm going to share with you also some new studies that we're doing right now that we have done on asperity concentration. And we can look at these studies together and see what can help us if we need to increase interface shear resistance. I'll share with you the next steps that we're going to carry on with in this asperity concentration aspect of texturing. We'll look at some, I'll present a summary of the whole presentation, and then we discuss, or you give me your comments or questions and answer at the end of the webinar. So the first aspect that I want to look at is, should we texture or should we not texture? There are two main considerations to pay attention to here if you want to decide if you should texture your geomembrane or not texture it. The first thing is, will the geomembrane be put in a situation where it will have to bear tensile stresses or be tensioned? We have to remember that the function of a geomembrane is to contain. So whenever we use it, whether it's textured or smooth, we have to ensure that it's not bearing stresses as much as we can. Another aspect to look at to make that decision is that geomembrane surface going to be a critical slip plane that may induce or make worse potential sliding of material? So a reference in this case would be the Kettleman Hills failure that happened in 1988. It was after the Kettleman Hills failure where a smooth HDP slid over slickened clay, like very, very smooth saturated clay, that texturing actually gained ground and we started texturing in the industry. So these two main considerations, what you have to look at if you want to decide if to texture or not. And then looking at those considerations further now, I broke them into different aspects that you may want to consider in further details. So the first thing to look at is check your slope angle and check your interface friction between the geomembrane and whatever material is in contact with it. So if you find yourself in a situation where your slope angle is greater than the frictional angle between your geomembrane and the materials in contact with it, then you're creating a situation where that geomembrane is subjected to wide width tensile stresses. And in that situation, the geomembrane now is acting as veneer reinforcement, and that's what can damage the geomembrane. That can cause it to rupture, or that can cause it to pull out of anchorage. So if you do find yourself in a situation where you designed for a 3-to-1 slope, however, something happened, and then you ended up with a 2-to-1 slope. Now your slope angle may be more than your interface friction angle between your geomembrane and whatever material is in contact with. If it's at this point, then you may want to texture the geomembrane to increase your interface friction between the geomembrane and the contact materials, so you don't put the geomembrane into that kind of wide width tensile stress situation. Another aspect to look at to decide if you should texture or not texture is check that along the geomembrane interface, if you're going to have a lower value of friction angle, make sure it's at the upper surface of the geomembrane and not below the geomembrane. Because what happens is if you have a higher friction angle over the geomembrane and you have a lower one beneath the geomembrane is anchored. So even though it's anchored, there might still be room for movement, right? So when the geomembrane is trying to move because of the lower friction angle at the bottom, and then it's anchored, so it wants to move, something is holding it in place, and then the friction angle above it is higher, you're creating tensile stresses within that geomembrane, and that can cause it to rupture, and that can damage it. So if you find yourself in that situation where your lower friction angle, interface friction angle, is at the bottom of the geomembrane, then you may want to texture the bottom so that you can make your upper geomembrane surface the slip surface in your system to change that. So another aspect of should we texture or not texture is an interesting one here, and is should we texture or should we not texture HDP geomembranes? When I was preparing for this webinar, I received an email from a renowned person in the industry who's done lots of testing on stress cracking of HDPE and has written lots of papers on the topic. And he emailed and he said to me, he said, are you going to mention to the industry not to texture HDPE geomembranes? And his position here was that as the textured HDPE geomembrane is doing its job, as the textured surface is trying to resist the movement, we may be creating stress concentration on the surface of the geomembrane that may induce stress cracking. The magnitude of the stress concentration, I don't know if anyone has ever quantified that, but that doesn't mean it's not a concern. It is a concern, especially if your asperity is higher, then you may have more significant stress concentration over the geomembrane surface. So when he asked if I was going to make that statement, I I thought about it and I thought, you know, he has a good point, but in reality, right, given all the few things that can happen on the site with your interface friction angle, in reality, for geotechnical considerations, I don't think that it's possible that we don't texture HDP geomembrane, right? What I think is that we shouldn't be looking at not texturing HDPE. What we should be looking at is how to manage the risk associated with texturing HDPE. So what are the risks? It's stress concentration on the HDPE, and number two, potential for stress cracking, right? And I'm going to share with us, after he asked me that question, I kept digging and kept looking, do we have the solutions already? How can we manage this? And we do. I think we do have the solution already, and I'm going to share some of them with us later on in this webinar. So how to reduce the stress concentration on the HDPE surface, and how to reduce the potential for stress cracking in the geomembrane too. So moving on now, if we find ourselves in a situation where we need to texture the geomembrane surface to increase the interface shear resistance, so again, our designs didn't go as we planned, or our slopes were designed to be something and then they ended up being steeper than they should be, and we really need a higher frictional resistance along the geomembrane surface, what can we do? What's going to help us? Should we find a material with the highest asperity in the world, increasing the asperity height? Or is increasing the concentration of the asperity going to help us, right? Those are the two aspects that I really want to look at in this webinar and share some findings and results with us to help us to make that concentration or decision when we get to that point. So what is the influence of asperity height on interface shear resistance? That's the first aspect I want to look at. I'm going to be referencing the study by Blond and Elie 2006, primarily for this aspect. There are several other studies in the literature. There's one by Nathan Ivey 2003. There is Stark et al. There's McCartney. There's so many of them in the literature, but I'm going to be using the Blond and Elie studies. And what they did in that study is they ran about 100 tests, large-scale direct shear testing of different textured geomembranes in contact with geotextiles and geocomposites, sand, clay, and some other materials. And they looked at the effects of density. So all other things remaining equal, if I was to vary, say, the density, HDP versus LLDP, everything else equal, is there going to be a difference in what I find with the shear strength? Also, they looked at the effect of the asperity height. All other things remaining equal, let's vary the asperity height. What's the effect? Thickness too, thickness of the geotextile, geocomposite, and thickness of the geomembrane. Was there any effect? And the materials that they tested in contact with the geomembranes were sand, clay, soil, geotextiles, and geocomposites. And the particle size distribution of the sand and the clay are in the top right corner on my screen. And then the attributes of the geotextiles and the geocomposites that it tested are in the bottom left corner. And it tested different weights of geotextiles and geocomposites, different thicknesses. So what did they find? To evaluate all the parameters that might influence shear strength, they plotted asperity height against the shear strength. They plotted asperity height against the friction angle and also against the adhesion. And what they found in that study was there was no significant influence of density on shear strength. So LLDP or HDP, if that's the only thing that's varied for two different materials, asperity height the same, thickness the same, then no difference in the results. Also, the core thickness of the materials tested, there wasn't any influence. What it did find was that there was an influence of asperity height on the shear strength. So smooth versus textured, or as you increase the asperity height, they found that the shear strength increased. However, they found that there seemed to be a threshold beyond which increasing the asperity height did not do much for increasing the shear strength, the interface shear strength along the geomembrane surface. And what they found was this threshold was between 20 to 25 mils of asperity. I'm going to show you some of the results now. So this is the result from the study for the geomembrane and geotextile interfaces. And on the left are the graphs for the peak shear strength versus the asperity height. So vertical axis is the shear strength. The horizontal axis is the asperity height. So we can see on the first graph there that there seems to be an increase of peak shear strength as the asperity height increased up until 20, and it kind of like peaked after 30. And similarly for the residual too, similar thing happened there. So after about 20 mils of asperity, there did not appear to be any significant gain in the shear strength that was measured. Also, for the geomembrane and the sand interfaces, a similar thing happened there. So there was a significant climb of the shear strength as the asperity height increased, but then after 20 mils, there wasn't too much to gain from increasing that asperity height beyond 20 mils. For geomembrane and clay, again, a similar thing. After about 20 mils of asperity, there didn't seem to be any gain in the shear strength that was measured by increasing the asperity height. So here is a summary from that study. So what they concluded was that asperity height matters, right, for all of the materials tested for both the peak and the residual, or maybe not really residual, maybe post-peak or large displacements. Asperity height does matter. However, there may be a threshold in the range of 20 to 25 mils of asperity, right, where you get the maximum, where you get the optimum shear strength for your textured material. And then they also found that the interface shear strength depended on the material, and all of the geotextiles tested exhibited the same behavior. So even despite the density or whatever the parameters that varied, all of them exhibited similar behaviors. So knowing now that asperity height may be limited to a certain range beyond which it may not gain much, it's essential for us to find the optimum value within the reported limit that can give us the best performance if we're trying to increase the interface shear strength. And we have to remember again that looking at the graph on the screen, that as you increase your asperity height, the cost of the material quickly rises. So it's essentially again to find the optimum value within the reported limit that would do what we want it to do. So if there is a limit for the contribution of asperity height to increase in interface shear friction, and we really need to increase the interface shear friction, what else can we do? And that is what drove us to start researching and looking at other ways of doing asperity, increasing the concentration of the asperity, decreasing the asperity height, and all of that. I'm going to be sharing that with you right now. So one of the processes that we came up with is this texturing process called MicroTextured, right? I give it the name MicroTextured. It's not a trade name or anything. It's just the way the texturing is. It's really, really small. So MicroTextured, and what do I mean by MicroTextured or microtexturing? Microtexturing is when you, I don't know if the picture is very clear on your screen there. I think I have a clearer picture on the next slide, is when you have all of your asperities very, very close together. So you have more asperity concentration per unit area that you're looking at. And then this then increases the surface roughness of the geomembrane, and it creates a wider area of contact with materials. And here is a better picture of the microtextured versus what we call the textured with a blown film manufactured process. They're both blown film methods. So you can see that with a microtexture, the asperity heights are a little bit smaller, and then they're denser together. So we've done a few testing on the microtextured, and we've compared that with a database of textured materials to benchmark and see how the microtexturing process with a denser concentration of asperity might perform relative to the other ones. So we did interface friction tests in contact with geotextiles and geocomposites, so GCL and drainage geocomposites. And we looked at stresses from 10 kPa to about 500 kPa, or I do apologize for the units here. Also, we ensured that the geotextiles and the geocomposites were hydrated during the testing. And all of the testing were performed as per the ASTM test method for large-scale direct shear testing. They were all performed in 300 millimeters by 300 millimeters minimum size direct shear boxes. So these were like large-scale tests. And what we found is that with the microtexturing process at an asperity height of about 17 mils, we compared that with other asperities those that were like 17 mils but not microtextured, so wider space asperity, and also some that were even higher than 17 mils. And the graph on your screen there is in contact with, this is the result for the testing in contact with geotextiles. So these are the peak shear strength on the vertical axis, and then we have the peak normal strength or stress on the horizontal axis. So the lines that you see connecting the points are the lines for the microtextured. So we did low, medium, and high applied stresses. And it's interesting what we found, because the microtextured or microtexturing process at an asperity height of 17 mils, right, was giving us shear strength values that were comparable to what you would get with, say, a 62 mils asperity, or even anything that was higher than it. So along the same lines, right? If you look at the one for the 62 mils asperity, which is the blue triangle there, it falls like right under or very close to what we achieved with the microtexturing process. So similarly, for the large displacement or the residual, the post-peak, again, the vertical axis is the shear strength, and then the horizontal is the normal stress or the normal strength. And then what we found again was, although the residual values were a little bit lower, the microtextured was able to achieve a comparable shear strength with the other ones that had a higher asperity than 17 mils. And here is a summary of all of those results, so for the peak and for the large displacement or the residual with the geotextile. So at an asperity, the asperity height is the first column on the left, and we have the peak friction, peak adhesion, large displacement friction, and then large displacement adhesion. We can see the microtextured or microtexturing process in the middle there, being able to achieve as high as what you might achieve with a 28 mils asperity in contact with a geotextile surface. Even the adhesion for the peak and for the residual were pretty similar as well. So it appears that with a microtexturing process, you can achieve comparably high interface shear strength at moderate asperity height in contact with geotextiles. So looking at the geocomposites now, the peak values on the screen there, 17 mils microtextured again. We compared it with, for this one, it was up to 26 mils asperity. And what we found again is with all the stress, the applied stress range that we looked at, the microtexturing process helped us to achieve more or a comparable shear strength as we would achieve with, say, a 24 mils asperity, or even the other ones. Like really, anything below that line is lower than what the microtextured achieved. Anything above that line is higher than what the microtextured achieved. So most of them fell along that line or even below it. So with a large displacement now, or the residual, with the microtextured, a little bit lower than the peak. However, again, most of the microtexturing gave us a comparable shear strength as you would have with an asperity height that's over 17 mil. So again, it does appear that with a microtexturing process, by increasing that concentration of asperity, you can achieve a higher interface friction at moderate asperity height, which I think is interesting for us to consider. So looking at the values now of the geocomposite, all of the summary now on the screen. So at 17 mils asperity, microtextured was able to achieve peak friction angles that were comparable to what you would achieve with a 23 mils asperity, or even something higher like 26 mils. And also the residual values and the adhesion values were also pretty close. Actually, the microtexture seems to have a higher adhesion than the other ones with a comparable friction angle, peak friction angle, or residual friction angle. So these are really interesting results, and this is what I really wanted to bring to our attention, to draw attention to make us look at this a little bit closer. So when I was looking at putting the webinar together, I found that there's a recent paper right now on actually contribution of asperity concentration to interface shear resistance. The paper was just published in December 2017. So, and what they found too was that asperity spacing had an influence on the measured shear strength, and that in contact with geotextiles, when you have closer asperities, you can increase your shear strength. So this actually kind of like corroborates what I already shared with us from our testing so far. And another thing that was interesting is they showed, or they found, that there seemed to be an optimum spacing between geomembranes and clay interfaces. We haven't tested on clay, but that's one of the next steps that we're going to look at, to look into this position a little bit more. So now back to texturing HDPE now. So the main concern with texturing HDPE, as discussed earlier, was the stress concentration that we might have on the geomembrane as the texture surface is trying to resist that movement, and this may result in stress cracking. So I thought about it like I said earlier. So what can we do? We cannot not texture HDPE, but how can we manage the risk? So having a higher concentration of asperity can help. So I have a schematic there on the screen where the asperity on the geomembrane surface are further spaced apart. That's the one on the left. So assuming 10% is what's covered. And then on the right, I have a situation where the asperity is denser. So let's assume it's 80% that's covered. So based on just general analogy now, looking at those two, so you have 10% versus 80%. if any one of them, so when they both undergo, say, under similar stresses now, with the 80%, you have about 1/8, you have 8 times more of the surface area of the geomembrane engaging in the situation. So you're distributing that stress over a wider area of the geomembrane. So each individual material or asperity is carrying less load. So the stress concentration on the surface of the geomembrane should be about 1/8 of the 1/8 times as bad as what you would have with a 10% asperity that's further spaced apart. So again, we can say that if the stress concentration is 1/8 times as bad, then we have like 8 times less likelihood of pushing that geomembrane, HDP geomembrane surface into the threshold that would constitute stress crack, right? So this analogy is just to say that to manage HDP texturing, we probably need to increase the concentration of the asperity so that we have more surface area of the geomembrane carrying the load. So the other concern with texturing HDP now is how do we manage the risk with potential stress cracking? So the first thing, which has been widely stated in the industry, is to use an HDP geomembrane that has a high stress crack resistance. So something that exceeds the GRIGM13, so greater than 1,000 hours, greater than 1,500 hours. And in addition to that, use an HDP geomembrane that has a reduced susceptibility to stress cracking strains. And the picture, the map or picture that you're seeing on the screen in the bottom there is a comparison of our GRIGM13 HDP geomembrane with a stress crack resistance of 500 hours, and then our Goliath geomembrane that has a stress crack resistance that's greater than 1,500 hours. Aside from the stress crack resistance of both geomembranes, the mechanical properties are also very, very different, right? And the picture is a strain mapping of the surfaces of both geomembranes. So this was developed after from a large scale strain testing. So this wasn't a puncture testing. It was done to simulate the response of both geomembranes to strains that may induce stress cracking. I wasn't going to include this in the webinar, but it was after that question on texturing HDP that I decided to bring this testing to share with us. So what we found with both materials was that the HDP geomembrane that just meets the GRMGM spec with mechanical properties and everything else actually had more percentage area exceeding potential stress cracking strains. So on the screen there, where you have blue is like, so it is lesser strain, and as the colors get lighter, you have more strain concentration. So both geomembranes were tested in contact with gravel, similar gravel. The applied load was about 800 kPa for like 9 days, so simultaneously, similar conditions, and this is what we found. So the Goliath was able to resist had a lower susceptibility to stress cracking strains than the GRIGM13 material. That's the whole essence of that picture there. And here is from that strain map. This is the strain distribution plot. It's like a particle size distribution plot, but instead of particle size, we're trying to assess the percentage of strain exceeding a certain value. And what we found was that the Goliath, the one that has a higher, better mechanical properties and the lower susceptibility to stress cracking strains, actually had a lower total percent area exceeding certain threshold strains in comparison with the GRIGM13 material. So what's the point I'm driving at here? So with HDP then, I think maybe we're looking at the possibility of an ultimate textured HDP or an ultimate way of texturing HDP, or if we have to texture HDP, maybe it has to be micro-textured in a way, or increase the density of the asperity on the HDP, and also combine it with an HDP with a resin that has a high stress crack resistance, right, greater than 1,000 or 1,500 hours. Maybe that's what we need to do with HDPE instead of saying do not texture HDPE. Those are my thoughts, and you can let me know what you think about that position after the webinar or later on. So the next steps now in our assessment of the contribution of asperity concentration is we've done all this testing. It's showing us something, but we're not going to stop there. That's not enough to just say, okay, that's it. We need to do more testing. So we're going to complete more interface shear testing on the similar test conditions on using similar materials and similar parameters. I have to mention that all of the tests that I showed you before, they weren't all done in the same lab. They weren't all done at the same time or using the same strain rate or same conditions. We did recent tests, and then we compared with what we already have in our database. So what we're going to do now is do more testing under similar conditions and see what we come up with. But I don't expect that it'll be too different from what we have now, especially since studies in the literature already are showing trends along that line too, that asperity concentration is actually beneficial for increasing interface shear strength. But we will do the testing just to get it done in a rigorous way. So another thing we're going to do is we're going to test the microtextured that have asperity heights greater than 17 mils. So we know that there seems to be a range for asperity heights up to 25 mils. So we're going to test 17 to 25 and see, can we even push this interface shear strength higher than what we're currently achieving with 17 mils. We're going to test more contact materials. We'll test sand, we'll test gravels, we'll test clay into the behavior. And also we want to look further into that position from that paper that was just published on optimal spacing with geomembranes versus clay interfaces with the asperity concentration. We'll look into that further. And we're also open to suggestions on what else you may want us to look at that might be beneficial for design. I received an email as well in relation to this webinar I got an email from another renowned person in the industry who I think he's been looking at how to characterize asperity concentration. Like one thing we have to do is for this microtexturing, how do we ID this material? If we want to specify it, how do we specify it? So that's something else that we may want to look at in our next steps. So to recap now, on texturing or not texturing, it's not a position of texture or do not texture. You have to look at your site and look at the conditions that you have on your site, and that's what's going to help you decide if you should texture or not. So a few things that you can check is ensure that the geomembrane is not acting as reinforcement, it's not being tensioned, and ensure that the geomembrane is not a critical slip surface. So how can you put a geomembrane in tension without knowing it? If your slope angle is higher than the frictional interface friction between your geomembrane and the materials in contact with it, you may be pushing that geomembrane into a position where it's acting like reinforcement without knowing it. So in that situation, you may want to texture. Also, ensure that if you're going to have a lower interface friction along the geomembrane surface, it's at the top and not at the bottom of the geomembrane. Usually, we always assume that once the geomembrane is anchored, it's not moving anywhere. But we have to remember that usually it's anchored at the top. It's not necessarily anchored at the bottom, so there might still be some movement along the bottom surface. So if we just texture the top of the geomembrane and we leave the bottom untextured, then we're increasing the interface friction above the geomembrane and leaving the one beneath it very, very low. So when that geomembrane starts to move now, the critical slip surface is going to be under that geomembrane. But because it's anchored, it wants to move, it can't move, it wants to move, it can't move. Then you're going to put that geomembrane into tension. So you have to check that. So you may want to texture under your geomembrane to prevent it from, to make your, if there's going to be any critical surface, to make it, to push it to above the liner so you can, your slip surface is above and not beneath. On HDPE, for geotechnical reasons, we just may not be able to not texture HDPE. We may just need to look at how to manage this risk. Number one, what is the scale of the stress concentration? How significant is it? What's the scale? What are we dealing with here? And then if, depending on how big of an issue it is, then we'll look at ways of managing it by decreasing the stress concentration in individual asperities, and also using a material that has a high stress crack resistance and one that has a low susceptibility to potential stress cracking strain. So yeah, I already said that. So I'd like to state first that whether you texture or not texture a geomembrane, you have to ensure that when you backfill over the geomembrane, you backfill from the bottom up. I got a few emails from the renowned industry experts that said, okay, one thing you have to mention in this webinar is, regardless of whether you texture or not texture, ensure, let them know that they have to backfill from the bottom up. So start with a large passive wedge at the bottom of the slope, and then work your way up from there. And that way you don't put the geomembrane in a situation where it's tension or where it's going to be tensile stresses, whether during backfilling or when you have movement, say you're in a seismic region, where you have a good passive wedge at the bottom, you might have some movement, but then that passive wedge is going to stop it from moving. So you wouldn't put the geomembrane in tension too badly. So finally now, initial results from studies are indicating that increasing the concentration of asperity may actually, we may be able to achieve higher interfacial resistance at moderate asperity height by increasing the concentration of asperity. So that's the webinar for today. On that note, I'm going to say a very big thank you for tuning in today, for joining this webinar, and we'll take some questions now. Thank you very much. Also, I'd like to mention, if you'd like some PDH credits for this, you can email us after the webinar. We'll send you some questions to answer, and then we'll send you a certificate after we've received the answers to the questions back.